Hello everyone, and welcome to Lesson 3. In Lesson 3, we're going to talk about polyatomic ions and how they fit in with what we already know about chemical nomenclature. Just like the name sounds, polyatomic ions refer to ions that are made up of more than one atom. You have a list of these polyatomic ions on the common ion sheet, which has been provided to you. When we take assessments, when we complete homework assignments, you'll be able to use these polyatomic ions in order to answer those questions. You will not be responsible for knowing any of the ions outside of the list that is provided to you. As we start to look at the rules for naming and writing formulas for compounds involving polyatomics, you'll notice the similarities to what we've already been doing with simple binary compounds and divalents. The only difference is that instead of an anion being a simple element off of the periodic table, now our anions are going to be composed of these polyatomic ions. So let's take a look at what we need to do here. The first part of this says to identify the cation and the anion. That's very similar to what we've been doing. The second step says to find the least common multiple and balance the charges. Again, this is no different than what we did with simple binary and divalent compounds. We're going to eliminate positive and negative symbols, and we'll reduce when possible. Let's take a look at our first example. We have sodium carbonate. Sodium is an element right off the periodic table. It's in group 1, so it's going to have a 1+ charge. Carbonate is our polyatomic ion. So if we check the list of polyatomic ions and find carbonate, we'll learn that carbonate is CO3 with a 2-. What we're going to do here is just like what we've done in the past. We are going to piece these two pieces together, canceling out the charges so that we form a neutral compound. Carbonate has a -2 charge. In order to cancel that out, I'm going to need 2 copies of my +1 charged sodium ion. So my final formula will be Na2CO3. Our second and third examples involve divalents. However, they're done the exact same way. So we're first going to identify the charge on the cation. So in this case, copper 2 means we have copper with a 2+ charge. Then we'll check our polyatomic ion sheet for the sulfate ion. When you do that, you'll find out that sulfate is SO4 with a 2- charge. And just like we've seen in previous examples, when we have the same charges, in this case 2+ and 2-, those charges will cancel each other out. So we'll wind up with a formula of CuSO4. If we take a look at our last example, plumbic iodate. Plumbic, if we look on our divalent cations on the left side of our page, we'll find out that plumbic is Pb with a 4+ charge. And iodate is IO3 with a 1- charge. In order to get these charges to cancel, I'm going to need 4 copies of the iodate ion in order to cancel out the +4 charge that I have on my lead. Because we need multiple copies of the iodate ion, we have to put that inside of parentheses. Anytime that you need more than one of a polyatomic ion, that must be enclosed in parentheses. In example 1 and 2, we did not need to use parentheses because we only had 1 copy of the polyatomic ion. Let's take a look at some more examples. It might help you if you wrote out the ions and their charges first before trying to put them together to form our compound. So in our example number 1, we have chromium 3, Cr with a 3+, and we have the acetate ion, C2H3O2, the the 1 minus charge. In order to get the charges to cancel out, I have positive 3 here and negative 1. I need 3 copies of this acetate ion. So my final answer is going to be Cr. Because I need more than one of these, I have to use parentheses, C2H3O2, and then a 3 outside of the parentheses, indicating that I need 3 copies of that. Let's take a look at our next example. We have strontium. Strontium is an element off the periodic table. It's in group 2, so it has a 2+ charge. Sulfite, that's our polyatomic. If you look up sulfite, we have SO3 with a 2-. In this case, our 2+ and 2- charges will cancel. We'll wind up with SrSO3. In our next example, we have magnesium phosphate. Magnesium has a 2+ charge, and phosphate has a 3- charge. This is one of those examples where you need to find the least common multiple in order to get your charges to cancel out. The least common multiple between 2 and 3 is 6. So ask yourself, if I need to get magnesium to 6 and they're each 2 positive, I'm going to need 3 copies of magnesium. So I'm going to put a little 3 next to the magnesium in the formula. If I need to get phosphate up to 6, right now it's -3, I'll need 2 copies of phosphate. So the polyatomic has to go in parentheses, and then a 2 will go outside of the parentheses. Example number 4 is one of those rare times when you see a polyatomic cation. That means not only is the anion a polyatomic, the one with a negative charge, but the cation, the one with a positive charge, is also a polyatomic. The polyatomic ion ammonium can be found on the left side of your common ion sheet. It has a charge of +1. Nitrate, found on the right side of your common ion sheet, has a charge of -1. +1 and -1 will cancel each other out, and we'll wind up with NH4NO3. Finally, in our 5th example here, we have cuprous. If you look on the divalent side, the left side of your sheet, you'll find out that cuprous is copper with a +1 charge. Bromate. Bromate is BrO3 with a -1 charge. +1, -1 cancel out. We have CuBrO3. I know just in this example I've switched back and forth between writing +1 or 1 positive. It really does not matter to me as long as you understand that the charges must cancel out. What really becomes challenging in naming and writing formulas is going in the reverse direction for polyatomics. It's often confusing to figure out whether the subscript is the number of polyatomic ions or just part of one polyatomic ion. So I'm going to point that out to you as we go through this. If we look at the instructions, they say identify the cation and the anion. And then for divalence, we're going to have to multiply the charge on the anion by the number of anions in order to try and figure out what that charge is on the divalent. Remember, divalents have more than one possible charge. I wrote, be careful when identifying the number of anions. It's easy to misinterpret the significance of a subscript, as I mentioned earlier. Finally, divide the result by the number of cations. So let's take a look at our 3 examples here. In our first example, we have calcium and we have hydroxide. This is a straightforward example. That's the name, calcium hydroxide. However, the problems get more complicated when we have divalence, like I'm going to show you in examples 2 and 3. So remember, with a divalent, there is more than one possible charge for that element. In this case, it is tin. Tin could be +2 or tin could be +4. How do I know which tin I have in this example? In order to figure this out, what you need to do is this. Divide up your compound into two parts. Start on the right side. Identify what this is. This is phosphite. You can even write that part down here. Now, the charge on a phosphite ion is -3. So you can write that up here. In this example, I have 2 copies, that's what the 2 means, of this ion, which has a -3 charge. So the right side is -6 overall. That means the left side has to be +6 in order for them to cancel each other out. This 3 means I have 3 copies of tin. 3 copies of tin that are going to add up to be a +6 charge. So if I write down 3 copies of tin, what must each copy be in order to add up to +6? Well, they have to be +2 each. So that means I have tin 2 phosphite, also known as stannous phosphite. In my third example, I'm looking at lead. Lead also has 2 possible charges. Again, +2 and +4. Which charge do I have in this example? So what we're going to do is we're going to break this up just like we did before. We're going to identify what this is. This is sulfate. My next question is, how many sulfate ions do I have? Be careful. If you said 4, you're misinterpreting the subscript as the number of ions instead of part of the sulfate ion. In fact, I have just 1 sulfate. And I know that because if I had more than 1, sulfate would be in parentheses. We don't see any parentheses in this example. So look at the total charge on the right side. The total charge is based on 1 sulfate, so it is -2. That means the total charge on the left side is going to be +2. In this case, I have just 1 lead accounting for that +2 charge. So I have lead 2 sulfate or plumbous sulfate. Let's try some of these examples. As we look at our examples, you'll notice that some of them have 1 line and some of them have 2 lines. Those that have 2 lines are the divalents and will have 2 different names, stock name and the common name. Those with just 1 line are elements off the periodic table, and we can just look up their name if we don't know it by looking at the periodic table. So in our first example, we have aluminum, and then we have PO4. So if you look at your polyatomic ions, PO4 is the ion phosphate. So the name here is going to be aluminum phosphate. Here again, we have an element, K, potassium, straight off the periodic table. It's not a divalent. So we can name the 2 parts, potassium, NO2. If you look it up, you'll find out that it's called nitrite, ITE ending. So this is potassium nitrite. In our third example, you see another element straight off the periodic table. In group 1, we have sodium, And then if you look at the other piece, the HCO3 minus part, that is called bicarbonate. Problems 4 and 5 have divalents. Divalents are more complex because now we have to identify what the charge is going to be. So let's start off by looking at the right side. CO3 is known as carbonate. So we can go ahead and write that part down. There are no parentheses here, so we have just one copy of carbonate, and the charge on it is -2. That means the left side of this is going to have to be +2, and thus, with only one copper holding that +2 charge, I have copper to carbonate, also known as cupric carbonate. Let's look at example number 5. In this case, I identify the polyatomic as hydroxide. Notice the parentheses. I have 2 copies of hydroxide. Each hydroxide has a -1 charge. Because I have 2 copies of it, I have a -2 charge on the right side. That means the left side has to be a +2 charge, and thus manganese with a +2 hydroxide, also known as manganese hydroxide. Alrighty, that wraps it up for polyatomic ions. Please complete and submit the rest of that assignment. If you have questions, please arrange a time to meet with me so that I can answer any uncertainties that you might have. Have a great week.